Um, let's see. It's time to start. So, good morning, ladies and gentlemen. Let me start this concluding meeting with you. First of all, I would like to stress that it won't be a usual lecture. There's nothing to learn for your examination. Rather, I would like to give to repeat what were the topics of the course, to give it to you in as a whole. Then I would like to talk a bit about why such a course, what I would like to achieve, what me and other instructors would like to achieve by giving this course, and what are achievements, and what are the problems we have to work against. Yeah, and then I expect some questions and some feedback from you according to the course. So that will be free discussion. I hope I will hear your voices. Since somebody could hesitate, I won't record the last part. I won't record our free discussion. Good, so let me understand where we are. We have finished the lecture. Homework is done. I believe that either today or tomorrow, the instructors will finish the homework and write them. The only future meeting is the exam. We have got a pre-examination, so you should be now aware of all technical peculiarities related to the examination. If you feel you don't, please ask questions about this. And that's it. That's one of the last meetings related to the course. Good. Let me perhaps get to the first lecture, to one of the first slides, and let me talk about the topics we have touched. All right. Overview of the course. As you remember, the lectures came in packages which were kind of rather different, which were complementary to each other. These packages are given in different colors, but let's not talk about the packages. Let me just go from first to the last lecture, what we did. First of all, we needed to refresh quantum mechanics. Although all of you got pretty decent quantum knowledge that was restricted to usual common quantum mechanics, which was basically about quantum mechanics of single particles or single quantum systems like qubits. This is not the problem set of advanced quantum mechanics. And we immediately got to recognition of the fact we talk about identical particles and understood how their wave functions are made and why it is so tedious, why it is so difficult to describe them with standard methods of quantum mechanics. So we needed some technical advance, which has been provided in the next lecture when we talk about second quantization. Basically, we have introduced creation and annihilation operators. We also understood the relation between particles and field. We talk about Fock space, all that together. So that was perhaps rather boring technical part, but we've done it. We got to the business. We got a set of tools to treat, to understand the problems of advanced quantum mechanics. Fine. Then we immediately turn to applications of these tools. And there were two lectures about condensed matter systems, about materials, if you wish. We looked at magnetism, we looked at superconductivity and superfluidity, where this method of creation relation operators appear to be indispensable. Right. In both cases, we've been talking about some new ground state, which differs from physical vacuum. We talk about unusual ground states, which had broken symmetry. That was also in magnetism and superconductivity, superfluidity. So it was something to supplement your solid state knowledge, perhaps. I don't know how much superconductivity you got in solid state. Surely you didn't have much of superfluidity. Anyway, but well, one could see it as examples illustrating the general framework of advanced quantum mechanics. Good. That was roughly about the particles. Right. We then turn to the fields. We turn to the classical fields. Because at classical level, there is, of course, a very clear distinction between particles and fields, which is absent at the advanced quantum mechanics level. Right, so we turn to classical fields. To feel the difference, we have taken many examples, and the goal was to understand that any classical field, whichever it's usual or unusual, can be seen as a large set of oscillators. With this, we could easily go to quantum mechanics because we know how to quantize single oscillator. We got excitations of this oscillator in terms of bosonic particles. So we can accomplish the problem of field quantization. And that was an achievement. We talk also about zero point fluctuations, about correlations of the fields, if you remember. It was very long and very important lecture when we talk about transitions most kind of a generic example of the transition was an emission of a photon by an atom in excited state. But we talk about transitions in general. There's many examples. Also in homework, you got quite some examples. We slightly touched lasers at the level of balance equation. In the next lecture, we have touched and, well, I would say rather trivial, but very interesting and constructive topic of coherent state or a bosonic field. Vacuum can be shifted to a coherent state, which is quantum approximation to a classical state of the field. Any classical state of the field has associated coherent state. And we also understood lasers in this way. We also apply this concept to solid state and to quantum devices, which can be in coherent states. That was it. Then there was an unusual chapter, which I find very instructive. To understand real world, one needs to understand dissipation that concerns our everyday life, where friction, dissipation plays important role. The same about quantum mechanics. So we understood how to treat the systems with friction in the presence, the systems in friction. And we have understood that it's not something which one can do in the framework of common quantum mechanics. Because a fricted particle, it's not a single degree of freedom. Rather, it's a particle immersed into an environment with many degrees of freedom. That's why you need advanced quantum mechanics for this. Good, so we have quantized an oscillator with friction. And then in the next lecture, we have considered more sophisticated systems, spin Boson model, where that was basically about transitions in the presence of dissipation. We talk about qubit in an environment, we made classification. We understood the concept of Anderson catastrophe, all that. And in the end, we got to a topic which is traditional for traditional courses of advanced quantum mechanics, something which you can get in Leiden or Amsterdam. We got to relativistic quantum mechanics. We did it in Hamiltonian methods to be consistent with the previous material. But basically, we have understood that relativistic quantum mechanics is also a case of what we have already studied. The only point which is important is to pay proper tribute to Lorentz invariance of all quantities coming into the play. That was the course. Right. I would love to have some response at this point. Can somebody ask a question, whatever, put something to the chat? or ask a question. All right, these were topics. And can somebody tell what is a topic he or she recalls least of all? Just, you look at this list and you don't actually remember whether you had it. Absolutely. Blackout. So what is a topic you remember least of all? Yeah, Jerry cannot remember relativistic quantum mechanics. That was the mere last lecture. So we talk about Minkowski space. We talk about Dirac equation. Yeah, understand if that you have been at this lecture. But yeah, I don't know. The story is that initially I didn't want to. When many years ago I composed this course first. I just didn't want to talk about relativistic quantum mechanics. So the idea was that, well, it's a bit not really very suitable in a technical university where people are concerned with practical matters. And relativistic quantum mechanics is rather far from everyday life, from everyday practice. So first I thought, well, I don't want to talk about this. But my colleagues kind of told me, no, that's not proper way, because even a student of technical university, and perhaps just because that it's technical university, student should hear about Dirac equation. First I resisted, but then I kind of appreciated this. Indeed, it's something relativity, Minkowski, Lawrence. It is so romantic. It just gives you a drop of romanticism in this life. Good. A question from Janine. I have difficulty understanding what second quantization actually is. Could you say in few words what does it mean? It means a method, right? We've been talking about identical particles. We have understood the structure of their wave functions. And in principle, we could do all problem sets with the methods of usual quantum mechanics. Just try Schrödinger equation for a zillion of components, but that is not practical. You cannot go far from this. So one needs another tool set. One has to navigate in this fog space with creation annihilation operators, has to understand a little algebra they obey, and how to implement this algebra in a course of practical calculations and calculations of practical quantities like energy, spectrum of excitations. Right? This is what we call second quantization, a tool set. That's been summarized in the second lecture in several in a table, and that's what kind of was necessary technicality to start working on the course. Good. From rule, I still don't understand what a magnum actually is and how it follows from rotation of the ground state. All right. Talking about magnons, perhaps it's easier to start with classical picture. I believe there was an instructor presentation about magnons, about magnetic oscillations. So you have a magnetization vector of a magnet, and you kind of can excite it with a magnetic field, so it will become to oscillate. These oscillations are if you quantize these oscillations, you ascribe a particle to it, bosonic particle, as you can do for any oscillation. These particles are called magnons. That's the way to understand magnons from classical field. What we did in the lecture looked a bit different. So let me remind what we did in the lecture. We took a magnetic ground state, and we understood that if we apply rotation, this state will be just the same. There's a symmetry, there's broken symmetry of the magnetic field. But if you rotate magnetization vector, yeah, it changes the direction, but it remains a ground state. So there were no excitations, there were no magnets. But there was a simple controllable trick to introduce this excitation. To this end, we made rotation axis of magnetization a little bit different in space. Actually, we modulate it with a sum wave vector. In this way, we produce not only the new ground state, but also an excitation, something which costs energy. In this way, we could get wave function of the magnet. We immediately understood that this function in fancy terms is an equal weight of superposition of very many electron Hall pairs. And we can compute the spectrum, so we also could prove that magnons are bosonic particles. So that was the same derivation, but with a different sign, with starting from particles. Does it answer your question, Rube? Very good. More questions about the topics? Right, then let me talk about the general idea of giving this course. Perhaps it's more complex topic than the advanced quantum mechanics by itself. Right. Universities. Although we are technical university, we don't regard it as under university. Indeed, you got university education, which means that you not only learn things, but you also learn how to keep them together. understand the links between different fields of science, understand the links within a field, and got some skills which would allow you to produce new knowledge, right? In whatever settings you can. You could go for a research job, pure research. You could go for academic job, then we also have to teach people. You could go to a bank. Anyway, a person with university education supposed to have some skills. Well, nowadays it's called innovation. Some skills which allow you to come up with new ideas to solve the problems nobody has solved before, and to understand the processes around you, whatever the process is, in a much better way, to see more individual things. That's kind of university education, you know that. If you just go, to newspapers, to what people usually talk about universities, it looks like universities are supposed to be innovation center, and they would constantly invent things which would immediately go to practice and would help our economy, and finally it would be good for everybody. Do you recognize this picture? I kind of exaggerate a bit, but is it what you think? Who can give an example of such innovation? An innovation which came from a university and in some years got impact on the economy and eventually made big number of people happy. It's something different. Is what I would say pure research, applied research, but pure research. I don't think it has anything to do with university. Many years ago, I was actually given some money, not like salary, but something which I could spend for equipment, for trips that came from TNO. Otherwise, I had no connection with this. I knew some guys who work at TNO. That can be good employment after all. Yeah, but it's not really university. And I don't think that, of course, most people which come to work to New York got university education. That's it. That's what I said. University gives you an ability to produce new ideas to solve the problems which otherwise nobody would solve. Quantum computers, that's a good catch. Do you see much of quantum computers around? It is an idea that in some years they will become important and perhaps a part of our everyday life, but that still has to come. frankly, I don't think I will live through. You might, yeah. Mohammed mentioned Bell Labs. It's also a pure research environment that existed for a long time and was good for American economy, and simultaneously it had a strong connection to fundamental science, not to the university, not to. There was a kind of rather a wall between pure research scientists in Bell Labs and university. Basically, let me put it frankly, if you're really a researcher, students only disturb you. You would like to be isolated from students, but from time to time, you miss them, you kind of find money. Let me get a student. I would like to teach somebody. That's a Bell Lab system. We also had similar system in this country, like even 25 years ago, we got Phillips Labs. We were also people work at applied problems and fundamental ones. Perhaps not the same people, but they work together. Look, it's all gone. There's no Bell Labs in a way they existed before. There's no Phillips Labs. It is true that kind of big enterprises, big companies sometimes support fundamental research, hoping that it will produce something valuable. That's what Microsoft and Google do with quantum computers. Right? Oh, that's a significant part in this research which comes from private funds. However, for big companies, it's like a charity or whatever, risk investment in investment. So it's not that simple. The universities, one can kind of listen to it many times, but universities still mostly for education. It has been kind of experimentally discovered that best education you can get from researchers, from people who are really do every day with scientific research. That's why we do some research here, but it is not like we invent new things every day. What is not stressed, but what is much more important function of the universities is the conservation of knowledge, which sounds extremely boring, right? Just conservation, preservation of knowledge which existed. It's like you perhaps remember ancient libraries when there were, infinite shelves with many books, and there was a special person, librarian, which kind of took care of these books. University people kind of do this job. However, nowadays, it's not really about storing information that won't make much sense, because there's so much information which is in free access through internet. Rather, it's a conservation of certain attitudes, certain tricks, certain muscles, which would make a person, perhaps not a researcher, perhaps not whatever Einstein, but a person who would live in this world in a certain way, in such a way that he can again solve problems, produce new ideas, produce new knowledge. And somebody after that could fill internet pages with this knowledge. But this ability is the most important part, and that's kind of that's what we try to conserve in university. So the idea that we transfer these attitudes to you. And that's kind of fits to the cause, I would say. The cause mentions some greatest advances of human spirit, one can put it like this, like understanding the relation between particles and fields, like whatever the Dirac equation or second quantization. But look, these advances are not new. Most of the stuff which I talk about has been invented many times ago. That was perhaps about 100 years ago already. That was like 80, 70 years ago. Dissipative quantum mechanics, that was only 30 years ago. So I myself was a graduate student by that time. For me, it's a relatively new still, but that was all quite some time ago. All this have been made by people with certain mindset, which use this tool set, and they know how to do this. They know how to do this. And in fact, if you're experimentalists or theorists, that doesn't matter much. You exercise some mathematical muscles. It doesn't have to be equations. You could kind of do math without writing letters. You could do it in your mind. But you have to do this. Why? Because concepts and the objects of advanced quantum mechanics are so alien. Usual type of thinking would never ever got a success in this. So you need certain skills, certain one can call it mathematical skills, and sometimes it really goes to back to school to your algebraic skills. But it is, let me look at it wider. It is a training of alternative thinking. If you kind of got through this course properly, you would become sort of aliens, extraterrestrial beings, which could simulate humans, but have some qualities which are absent by ordinary human. That's the ultimate goal of giving this course. If you recognize this, if you do you also have such impression? Do you understand what do I talk about? I look what I do. I stop record.